So my name is Veljko. You can call me Vex. I'm a professional mobile apps developer for about 15 years now. Since 2018, I've entered the world of Bitcoin. Believe it or not, it's open source program written in C++. To be quite frank with you, I didn't know that since 2018. And then when I started to research, I figured it's a very huge thing, especially when we're saying about C++ and the whole stuff about it. Today we're gonna walk through as this is a very huge topic to the extent where some people actually write the books about Bitcoin and they can hardly tell anything in more than 100 and 150 pages. So we'll hear this, I'll just give you an introduction and some of the concepts described here. Often, Bitcoin is misunderstood quite a lot, and its connections to the general economy and some economical theories that we'll see may pose some actually something quite different that we have seen so far. Also, we will touch base on the soccer and the finances and current and traditional finances, as we will see it's pretty much everywhere. And we will talk about the networking concepts, because Bitcoin is purely distributed system. And in that domain, it has its own gotchas. We will see and explore what networking is. Also, because Bitcoin heavily extended uses cryptography, pretty much all the aspects of it. I will show you a really basic introduction and key concepts of some cryptographical stuff. Pretty much all of the things that we will go through will be employed in Bitcoin. Then we actually will go through the code walkthrough. So I will show you some meaningful classes. So we'll go very deep below and see how all this stuff is actually implemented. Lastly, I'm going to give you some closing thoughts and some directions of where the whole Bitcoin community is going. Before that, I would like to introduce you to the whole project. Later, we will see the code base. It all began in 2009, as we may know. It spins around that thing called Satoshi Nakamoto. I'll tell you a little secret. It's nobody. It's just a group of people standing behind the Bitcoin code base. And it's actually quite simple. We're speaking about open source software, which is licensed to an anonymous person. That's what Satoshi Nakamoto actually is. And that's legitimate way to do. We can all publish the software that way. So to begin with, we will go through some very elemental theories and practices inside of economy. Economy is basically a science and it's present pretty much everywhere in the world. And it's to some extent, as I've said, connected to Bitcoin. There's a little bit of timeline of how we, from the scientific point of view, observe the economy. We'll see what the theories are saying and what the practice actually looks like. Before the 16th century, economists considered that people have pretty much been doing things in what they call unstructured way. Rarely a few of people of that time have been observing economy as from the scientific point of view until this guy came up. It's called Jean-Baptiste Colbert, which is a French guy who spoke about thing called laissez-faire. Pretty much, and at least in the economical books, he is the first one who, again, moved and shifted away from that unstructured way to a little bit of theoretical observation of the whole economy. The whole point of the laissez-faire is basically that no government intervention should be, and that the market should simply float on its own, having its own dynamics, and with as little as interference as possible. We'll later see what Milton Friedman in the 1970s wanted to say with the deregulation concept. But before that, we should mention what's called the grandfather of theoretical economy, Mr. Adam Smith, who originated in the 17th century, in the 18th century, excuse me. We are expanding that, not necessarily connected to the concept of Jean-Baptiste Colbert, but he's known as basically father of the concept called free market. That's what we study in universities across the globe, simply as a reminder at how long the economical theories are in place. Of course, it is worth mentioning with the Adam Smith itself, he was a ethical professor of ethics, and later on he became the very first governor of the Scottish Bank. Aside from that, he was known for his pretty much the biggest, maybe the book in economy called Small Inquiry into the Wealth of the Nation, or shortly called The Wealth of the Nation. And there was a one book before it that he wrote. It is a theory of moral sentiment, where he debated or tried to philosophically approach the concept of a free market and basically had a little doubts about it. But that's a different subject now. In the meantime, there are many economists and theorists worth mentioning. Some of David Ricardo, Brian Hume, amongst many, many others. And as I've mentioned, back in the 20th century, this story didn't stop. The Milton Friedman, who proposed that deregulation thing, basically continuing the whole practice of for several centuries, who is proposing that free market stuff. Lastly, but not the least, we have one mathematician here who won the Nobel Prize, and it's Jonathan Forbes Nash. You may see him in a documentary about him, as he was actually studying game theory, and he tried to put a little bit of mathematics, maybe the first who actually tried to uh, sustain the dynamics of a market through the game theory. He won the Nobel Prize for economic theory, and believe it or not, he had a mental issue who he battled with the whole his life. He died in a car accident in 2014, if I believe. Now, he's also connected, not necessarily him, but the game theory, because some observers think that Bitcoin whole theory, having in mind that it is a finite amount of coins, we'll see later what that means, this could be a representation of a new economical thought based on the game theory. Speaking of that, just it's worth mentioning that one thing is economical theory. The second is, as we'll see a bit later, is a finance. Is the third thing is the banks. It's all somehow blended in the thing called economy. And on the top side, we can see the theory. Excuse me, the practice. The practice by some economics theoreticians begin with the East Indian Trading Company. That's 17th. That was a company that some believe was gave the birth of the global corporations because it employed more than 14,000 people. It had a fleet of ships of 12 different ships that were transferring the goods and services pretty much all across the globe. Speaking of free market and the non-influence of traders, I have first what some economists believe to be a bubble. Yeah, we in the IT industry know that from the 90s, that's economic crisis or financial crisis. Men believe that this is the first one, being done in 1637. It's called Tulip Mania and it's connected to the East Indian Trading Company. Basically, the whole story goes around that people can actually influence the market by not necessarily supplying certain goods, and therefore evoking a bigger price. That's called the goods shortages, or sometimes known as the crisis. As the story goes on, we have a Danish state bankruptcy back in 1813, where the whole country proclaimed the collapse. It was basically 200 years ago. Something that we might know as a Black Friday. That's 1869, basically, and 19th century. We know that as a today, as a sort of series of discounts, but that's actually the whole story is connected to the gold rush and that whole idea of digging the gold in the United States, really mid 19th century. Then we'll speed up the things because we had the Great Depression before the Second World War. We had the Wall Street collapse in 1929. And a whole bunch of crises, starting from the gold crisis, Russian crisis, Yugoslavian crisis, Indian economic crisis, Norwegian bank crisis again, and so on and so forth. Lastly, hopefully that will be and was the last. You have a so-called financial crisis or the housing bubble back in 2008, with some believe that actually the Bitcoin, who emerged a year later, sort of underquote responsible for all this sweeping world of economical theories and practices. Ways. This is a nice depiction that some economists use to sort of explain all the subtle differences. Now they call this economical wedding cake uh, graph. At the bottom layer, we have economical terms, economical players. That's us. He used to call us buyers, consumers, producers, sellers, whatever. And these are all the goods and services the economy, just some of them, of course. We have food, transportation, music, telecommunications, some of the services such as gyms, going to theaters and stuff like that. This is, without going a bit further, economy assumes this bottom layer as a regular day-to-day parts of our lives. And then this is where the distinctions between the finances begins. Finances are part of the economy, but just on an upper layer. They more narrowly observe the world of cash flow and money, and they do not use the terms such as buyers, suppliers, and consumers, but rather something of cash flow, financial flow, costs, operating costs, profits, and all that we have probably heard many, many times. That's one distinction, first in terminology, and second in the domain of the whole science. Like finances do not necessarily observe markets, but are an internal, let's say, cash flow or investments of a particular company. Plus, it is worth mentioning that we have a private finances. Each one of us basically has its costs, earnings, and salaries. That's how we term it from that perspective. On the right part of the wedding cake, we have a distinction between what the economy calls production, like goods, and on the right hand side, we have a services. That's something that's part of the economy. They do not produce what the economy calls a new value, but rather they offer us some services that basically we can mm, to do or do to ourselves, such as healthcare, security services, education, law, and stuff like that. On the top of the wedding cake, as we can see, we have banks and only banks. Banks is the following terminology: loans, credits, accounts, balances, and they are regulated pretty much in every state by a thing called central banks. They do not necessarily pay attention to costs and earnings, and they keep our accounts and balances for us and for all the other companies. This is especially important because Bitcoin deals a lot with that transactions and fees, which will be observed through the mining fees. We'll speak about that. But one of the role of the banks is actually to control the money flow. And most of the countries, as we may know, they print the money. You have heard stories about printing money and all that. Business speaking, that goes through a central bank, through the banks, that then disperse all the cash of the entire economy. Bit for the wedding cake, finally, economy holds a macroeconomy, an individual, each of these economical things inside every company or bank or our private life called microeconomy. We'll see how Bitcoin impacts all of that. From the global perspective, this is just an illustration how the banks basically connected themselves through a banking network, and all the money flows through their accounts. Of course, we're speaking about the legal money. Of that many computation accounts and everything, one would ask, where's the software and all that? We will see. It's, as I've mentioned in the beginning, it has it's a possession. Try to give a little bit of a historical overview once again. To open off, there is a company called American Express. It's founded in 1850. So it's again mid 19th century. And I won't go too deep. It has its problems back in the early 90s and 2000. In some country today, it's actually banned and it cannot be used. But starting from the 1950s, 50s and on, we are witnessing a huge expansion of the whole software industry, computer sciences, and later on the IT industry, as we may know after the 2000s. events that happened. I have just outlined a few of them that may be of our interest here. So we'll start with Visa Incorporated. That's a card issuer company. We'll see the impact a bit later after the 2000s when we have entered the age of e-commerce, internet payments, and everything that we know of today. So it's a pretty old company that was there before the computers entered the mainstream market, so to say, which by some could be mid 90s or mid 80s, early 90s. For now, we do have a COBOL. You've heard of that programming language. I'll explain how and why it's connected to our world monetary system. This is some code that's actually written in COBOL. And people had some of these companies had a problem, let's say 2018, 2019, to find COBOL programmers because basically no one codes it COBOL anymore. And they needed to pull the people from their retirements just to put them back to fix the financial system. Anyways, in 1966, we have a MasterCard that has changed its logo a couple of times in the meantime. In 1985, as we know, we have a C++. 1975, Microsoft says 1976, Apple. Apple is now also in the game of providing their financial services through the system called Apple Pay. You probably know about that. Microsoft is there, not that much present, but it has its say when it comes to the internet payments, primarily because Microsoft can be considered as a pioneer of the home computing, like PC era and Windowses and all that. Then also, it may be known as producer of Excel, like that's a financial software that we know, and it's used pretty much like both in the commercial sphere and in the banking software, like financial insurance companies and so on and so forth. It's very flexible and people do love it. Then 1994, we have Amazon, eBay, we have Google and PayPal, all of which now constitute some portion of the global financial network and provide the appropriate services. 1991, we have Linux. 1999, we have Boost C++ libraries. If we disregard the COBOL, if you pay attention, this bottom row is C++ only. And some of these stuff are actually used in global finances. For instance, some of the servers in payment providers are based on Linux, of course, and tons of other C++ servers. Um, I will end this whole pretty, I'd say, self-explanatory graph with the following things. After 2011, we have AliExpress, which is also in the world financial sector. It provides the platform where we can buy goods primarily, but it changed a lot the way how we operate on a today's level. Bitcoin, as we said, came out in the 2009, as well as the Redis, as we know, it's one very popular storage mechanisms. So I'll give you just a quick overview of how the credit card companies operate. As I said, American Express was founded in 1850. It has a net income of $8.33 billion back in 2023. MasterCard was founded in 1966. Today, in 2023, it has $11.1 billion of net income. They have many what called derivates and other companies, one of which being Payoneer, which is direct descendant of the MasterCard. And I've left this list pretty open and vague as we have tons of other companies and internet providers. So our map nowadays looks more like this. As green dots are actually IT companies, and we can sort of divide them into following groups: credit card issuers, payment processors, uh, and providers of the payment services, not necessarily banks. Uh, there are a couple of companies nowadays that they issue their own card, such as mentioned Apple, who has its own Apple card, and Amazon that we can use to shop or do whatever. And our wedding cake has been expanded because in the middle of a financial domain, we have IT companies or providers of the financial services, and they with their own costs and everything that goes in the financial domain. Now, when we speak about the software, when half of the stuff is open by the GitHub, there's more than 4 million open source software today. Many of them we have spoke about here today. And as we will see, Bitcoin is also open sourced. But before that, how it all began, like if we wonder what is actually an open source and how that looks like. So it has, of course, its history. As I mentioned at the beginning, it all started in the United States where people were like, okay, we're a free society. We want to utilize our freedom of publication, or freedom of rights, whatever. And they argued that software in original forms, like in the 60s and 70s, was actually printed out. So the medium was a paper. And as such, it reminded, for instance, of other forms of publication, such as magazine, books, and whatever, which was available to any American citizen. And it's Dr. Richard Stallman who actually pioneered the whole approach and was one of founders of a Free Software Foundation. That's a nonprofit foundation that basically cares or trying to advocate the open source philosophy throughout the world. The whole practical level of this comes down to issuing or having the software licenses that we may know or have seen in our careers. I'll just name a few because list goes to more than 30 different licenses. We know about GNU, GPL, MIT. Bitcoin is licensed under MIT. We have Apache licenses, many of them. They vary in their permissiveness level, meaning what the end user is allowed to do. Basically, we can do three things. We can possess open source software because it is assumed that our computers are our stuff and we have all the rights to possess them. What's inside them is also a possession. So that's the first right of the software, free software possession. The second is a right to modify it. Like, because it's yours, like technically speaking, you can modify it. That's inherent right of every open source software. And third, very lately, is the right to actually commercialize it. Why we will never be arrested or sued by using or selling free software? Because it's allowed. Very simple. So that partially explains why someone is selling the Bitcoin under the whole crypto stuff. And technically speaking, we're all allowed to do so, given that we have read the license agreement that is pretty much attached to every single software. Later on, I will show you how it's done in a Bitcoin world. So to dig deeper, as we know, the networking is a fundamental part of every software development nowadays, especially in my field where I come from, the mobile apps. So sometimes the network is there, sometimes it's not. It's 3G, sometimes it's 4G, sometimes it's edge. So sometimes it can run out of the battery and all other stuff. So the networking, not necessarily in mobile world, but basically everywhere, is a giant topic. Of course, it relates to Bitcoin again. What we know about networking is pretty much known since some of the protocols exist for about 20 to 30 years and have been part of the RFC standards, and we have used them on a daily basis. So it won't be too much speaking about them today. We know that there's several types of connections. We know that there are several internet protocols available, one being Tor. All of these ones, IP4, 6, and Tor, are supported by Bitcoin. We'll see how. And Tor, if some of you know, has a close connection to the American Navy. Basically, Tor is the Onion router. It's an acronym. The Onion is communication protocol. It's a heavily encrypted layer with more than 4 different encryption layers before the data. It resembles the onion that you would cut in the middle, and you can see a picture somewhere on the internet. Networking also, as I've mentioned, can be encrypted or not. In the world of Bitcoin, pretty much everything is encrypted, especially on the networking layer. And that's something that on a daily basis we use and we see as an HTTPS. That's encrypted connection. Behind it, the scene, we have TLS and SSL, yeah, which I won't be going through, but that opens up the doors for the cryptography we'll see in a second. Aside from that, we have what's typically assumed as a request response paradigm that we know of, or server client paradigm. This is what opens up the door for someone to argument that Bitcoin is decentralized. It's distributed, not decentralized. This may end up being a centralized system where we have central server and many, many clients connecting to the same spot. From the point of security concern, today we know about flooding, DDoS attacks, the security leakages, and all kind of fancy stuff that could go wrong when just dealing with the network layer. Again, Bitcoin heavily takes care of all the networking and security, and we'll see how. This is a bit different approach that we know as a distributed system, or commonly known as peer-to-peer. Compared to the traditional paradigm, the nodes, these white circles here, are actually not connected to each other. And as such, they fabricate the entire network. The advantage of a distributed system is that each node does not have to know about all the other nodes, and each node has its what's called node traversal. It's a whole theory, basically, introduced by one of the computer science guys called Dijkstra. He invented the A-star algorithm. You may know that as a pathfinding algorithm. And he sort of established the fundaments of distributed system, primarily distributed storage and distributed computing. There's a whole story about how the things you can distribute over network. In our particular case, of course, Bitcoin uses both these approaches. It stores the data like in a distributed manner, and of course, it does a computation heavily distributed that we know as of mining. Some of the distributed systems that we may have had chance to use in the past are current Napster's SETI at Home, which is a program done by Berkeley Institute. All the users could have downloaded the simple graphical user interface that helped Berkeley Institute map, believe it or not, whole universe. That was a very ambitious project. And volunteers all across the globe could have helped basically forming a giant um, distributed computing network. Of course, Bitcoin is its in distributed nature. We will see that later. As I mentioned at the beginning, I will give you a very basic cryptographic like entry to the whole world. Cryptography is basically a mathematics behind the scene and is used for various different things, primarily for encryption, decryption, hashing, digital signatures, and many different things. It ensures data integrity, privacy, authenticity, and many different things when we combine all those aspects together. Here are just the basic introductions, like what the cryptography is, as I've mentioned. Like here on the left, we see some of the um, like domains of what cryptography actually does. As I've mentioned, it does encryption and decryption, hashing, which is quite extensively used, for instance, in the Bitcoin wallets. There is a whole story about blocks and stream ciphers, and cryptography takes special care about ciphers. There's a key exchange, key hashing, authentication encryptions that we can use when we authenticate the users. There are special two forms of message authentication called MAC and HMAX. We'll address them in a bit later. And a special type of hashing for, let's say, the password hashing. I will mention later an algorithm called Argon, which is proclaimed to be the best password hashing algorithm currently in the world, and he won the first prize for that back in 2018. On the right-hand side, we can see that mathematical ground or mathematical basis of the cryptography, where all the arguments actually come from. Cryptography does not claim anything; it proves the things. The whole point is to familiarize with a thing called mathematical difficulty and a special subdomain called hard problems. It's a domain of theoretical math that originated back in 1920s, where some mathematicians figured so-called P versus NP or P slash NP problems. P in this context being a problem, very broad and uh, pretty vague understanding of what the problem is. Again, it's just a mathematical theory. The second utilized constitutes NP or N versus P. And it all comes down to, and it's heavily connected to a pure number theory. That's, again, part of the mathematical uh, theories that primarily deal with prime numbers. Prime numbers are of special importance in cryptography simply because they're a little bit different than all the other numbers. And there's a thing called prime number factorization problem in mathematics that I haven't outlined here. That basically, just on a basic level, confirms that there is some mathematical equations who are mathematically hard to compute. Knowing that, cryptography basically hides behind that fact and leaves all the mathematicians to deal with it. Meanwhile, knowing that no one on Earth can actually solve some mathematical equation, cryptography heavily uses that to secure some stuff. Also, the big talks in cryptography spins around what's random. And as we know in computers, there's no random things, only pseudo random numbers. So mathematical randomness isn't the computer randomness. So we did a bunch of great effort on the computer science level to bring that true mathematical randomness inside of computers. It's especially important for example, on the hashing side of the stuff, where you try to find a sufficiently large prime number who's almost random, and you put it in some encryption and decryption algorithm to get an extra safety. Again, on a very, very basic level. Also, there are some like defections in the cryptography, what's called the one-time pad and forward secrecy. This is what cryptographers try to achieve. Every cryptographical system can be designed, but of course, we miss or try to play with some of the mathematical theories, we may end up being uh, producing a very bad or almost unsecure cryptographical system. As mentioned, we on a practical level, maybe on a daily basis, we use some of these stuff, as we know of TLS or SSL, SSH, for instance, or Open BGP suite for anyone signing their commits or doing similar stuff. And actually two more mathematical concepts are elliptic curves. That's curved planes, so to say, on top of which you do some calculations so that you get some, again, cryptographic arguments, such as your cryptographic system is secure enough. Like, again, on a very basic level. Only, or in other words, you take computation of elliptical curvature as a difficulty, basically. And again, in a very, very shallow understanding. To the extent where in the whole game is NIST, that's National Institute for Standardization. That's the body in the United States who actually follows all this. And from time to time, they standardize certain algorithms, cryptographic algorithms, on a worldwide level. Lastly, we have a Diffie-Hellman key exchange, which is also one of the concepts of the cryptography. That's what we use basically in every request that we do over HTTP connection. If you have time, try to dig out when the Diffie-Hellman theory emerged. Now, a little bit deeper, again, very basic approach into encryption and decryption. Some cryptographic books say that the very first encryption could have been found on the Roman ages. And it's a famous Caesar cipher. It's an example of what's called a symmetrical encryption. And apparently, Guy Julius Caesar used that to command or send commands to his army generals on the field. Messages were encrypted. Basically, the whole point of encryption and decryption is to find that key, which is actually a key thing in cryptography. Key is basically a number that you use to transform certain input that is called ciphertext. And I've given an example, just a pretty trivial one, how you can transform ABC into something that at the first looks quite random and pretty much like a nonsense. No, it's actually behind it is a message that we use uh, that we want to send over what's called an unsecured channel. The opposite way of decrypting stuff is again transforming this HD, YZ, whatnot into the ABC, the original message. Encryption and decryption algorithms. It's a again huge topic. I haven't listed any of them here, but just I want to give you an example that one key can be used to encrypt stuff, completely other can be used to decrypt stuff, and that's called a public key cryptography. There's connection between private and public keys, and they do get calculated on the fly using certain mathematical transformations, allowing us all to sort of have what's called the asymmetric encryption. So encrypting something with one key, decrypting it with the other. As I mentioned at some point, we have specifically designed authentication encryption mechanisms. They're called MAC and HMACs and are, again, pretty much a standard way, especially when we deal with brokerage software or stock exchange that requires a high level of confidentiality. Hashing, as mentioned, is a way to transform certain input into a specified output length. It's a kind of a very weird thing. And it's again a question of crazy mathematics behind it. Mathematicians call that one-way functions, and hashes or hashing is well probably quite a lot of use. In many languages, we do have an interfaces or protocols that allows us to conform our data structures and classes into something that we can express as a hash. We may use hash tables to speed up our data structures and algorithms, our computations. Hashes are actually behind the scene how every SQL engine has implemented the thing we know as indexes. And there are many different algorithms that perform hashing transformation. The key thing with the hashing that once you try to change the input, let's say from ABC to ABF, you would get quite the opposite output. And sometimes we use in, let's say, cybersecurity, the hashing as a way of confirming some identity, allowing us not to know who that actually is. This is used in a Bitcoin because every wallet address is actually hashed twice. So to completely remove all the traces of like anything that could resemble to human being, Bitcoin is very secretive about its users or us, and it uses hashing extensively. With the hashing functions, they can be designed again, and a few things have to be considered, like a hashing resistant uniformity, again, that mathematical difficulty, and some other attributes, because some algorithms, such as MD5, has actually been broken, so to say. It's a bit outdated, and it may produce certain collisions if we use it. It's better not to use it, basically, nowadays. We should consider the SHA family. That's closely related to something called RSA, which I won't be addressing today. And we have many different ones, such as XX hash, city hash, Girder, RIPE-MD, 160, and so on and so forth. Probably I've extracted two that you may find familiar. This is a base64 encoding or hashing that we may use sometimes to transfer the data in specific byte length, which is, as I've said, one of the attributes of a hashing function. No matter how large the input is, you will always get a fixed number. That's called bit length, and it can spawn from 5860, 5864 up to 512, and in some experimental cases, up to 1024. So it's a number that has 1,000 digits in it. Anyways, password hashes, as I mentioned, Argon, Bicrypt, and Scrypt are some of the that are used today. Argon being the winner. So it prevents something that's called rainbow and dictionary attacks. It's a different topic now, and is primarily used for hashing passwords, like further inputs, because of that one-time pad and all the other things on a cryptographic level. So it's free to use. It's open source, and feel free to consider it next time you have to deal with passwords. Keys, keys, as said, everything spins around them. We have a couple of different ways to observe the keys. Elementary, there are just in numbers, as we said, and they are placed inside of particular algorithms so that we can get that output. There are some variation or computational methods called key derivation and key creation functions, both of which we will see in a Bitcoin. And Bitcoin heavily uses public key cryptography, which I won't be going through today. This is just an outline. As mentioned before, we have possibility to encrypt different stuff with using private or public key. We will get different results. And knowing that those two things are connected on a key level, like every public key basically contains its private key. And again, some of the things that I mentioned earlier, the topic is so huge that we can speak about symmetric and asymmetric keys, therefore symmetric and asymmetric encryption, but we won't be doing this today. A few more things worth noting: that if a key gets compromised, like we can forget about all the basic maths and all the algorithms. Simply said, if I get to know your password, I can get into your Google account without any hacking or password guessing. So there are methods how the keys and the secret stuff in our code bases can actually be secure. We should be creating the keys, not storing them in some environment variables and then read them when the program starts. We should be making them in our programs. One last concept of the cryptography is called the digital signatures, or a whole story about signing. Signing may not necessarily be encryption. It may be, but I won't be going that path. It's a combination of several different aspects, such as key generation, signing algorithms, signature verification, and key derivation, for instance, for validation. Digital signatures are basically an addition to, let's say, a data. Imagine you have a file and an extra file with it, where it's only the signature that is contained. That way, you can, let's say, claim that certain data belongs to you. You have signed it, basically. A signature. We had some different lectures. We will understand how they represent that identity. And when you sign something using your public key and cryptography, it assumes that, okay, that's authentic now. That means no one tampered with the data. I've mentioned digital signatures. They are partially in place during the uh, en- encryption used during the authentication. I know it's too many different words and jargons, but that's what cryptography is. So I'll skip that again. Signature, as I've said, signatures generally, uh, they play with integrity and authenticity, and basically helps us make sure that no one changed the data. Some of the known algorithms are RSA, SHA family, ACDCA, which is we will find in Bitcoin, and something of importance here. Just recently, in this year, July 2024. NIST again proclaimed what first to be known a quantum resistant signing algorithm. I will address in a second what a quantum cryptography is, but it's worth noting that we have been given, and it's all also open and accessible to everyone, a first quantum resistant algorithm that we can use is called Falcon. The next one is Sphinx Plus, which is still sort of in development, but hopefully it will be approved. Falcon is approved by NIST. Quantum cryptography as the last piece of this section. is, let's say, relatively new stuff. The emergence of the quantum computers, at least on a theoretical level, may be connected to emergence of the quantum theory and quantum mechanics. That's around 70s. But it's around early 2000 where some of the quantum computers showed up, especially after 2010, because IBM, Dell, Amazon, they're heavily involved in it, and many other companies. Mentioning Amazon, they do offer a public computing services, quantum computing services follow us to sort of grant inside their AWS platforms. When it comes to quantum cryptography, we have to distinct quantum computers, quantum computing, which is again mathematics, quantum theories that are, some of them are explained on the right hand side, what quantum spin, what quantum quints and quantum entanglement is, out of which we can derive a quantum cryptography as a even harder or more difficult way to compute certain stuff. It's based mostly on statistics and probability, and it implies different mathematical structures than, let's say, traditional cryptography. And again, everything spins around computational complexity. Uh, some proponents of quantum cryptography are warning that until the Falcon came out, we were in a high danger because theoretically all the quantum computers could decipher everything that we have encrypted so far using the current algorithms. But that nowadays it's just not the concern anymore because we can hide ourselves between the quantum algorithms. In short, you know who said this? So probably this what we've been waiting for. Now we will go through a little bit of code as we're all developers here, and I will try to sort of reflect everything that I've said here inside of Bitcoin codebase. So this should be seen, right? Right. Okay. So how all of these things actually looks like in practice. So we can find a Bitcoin at the GitHub. It's open source for about years now. I'll start with hey, could you zoom in maybe? Just yeah, zoom in. Yeah. This. So I'll start with explaining something straight at the beginning. Okay. We have pretty few repositories available here. Few are pins called Bitcoin Core, which we will be going through, and BIPS. That's an acronym of Bitcoin Improvement Proposals. Basically, there's a working group called Bitcoin developers who take cares of several improvements, like on a whole project, mainly in the terms of cryptography and everything that I've mentioned previously. Until recently, they have published security patches, so to say, because Bitcoin wasn't 100% secure. And that group revealed what they patched in the previous version. The whole plan is to like put everything out in the public, which is fixed and secured by the December of this year. And you can find you can track that in BAPS repo. So when I've mentioned the licenses, let's see how this license looks like. So it's MIT license. It's licensed to the Bitcoin Core developers. So that answers the question: who's behind Bitcoin? Bitcoin developers, and they are dividing the core developers and just Bitcoin developers. All of them claim the copyright since the very first day, and I'll show you later of how that is done on the Satoshi Nakamoto level. The MIT license is probably the most shortest one out there. And as we can see, permission is hereby granted free of charge to any person obtaining a copy of this software, and so on and so on. And this and American legislation, when we have upper caps, it's like you're shouting. You're trying to like announce to everyone, to everybody, and that you're not you're not you won't have any damages. You're not liable for any sort of claims or damages or any tort or otherwise arising from in connection of using this software. It's a little bit of log practice here, but as we can see, we can fully use this software without any problems. So what we hope this is okay. What we're actually looking here is some would say typical C++ file tree. We have a CMake and everything that goes with it. We have a readmes, installs, and security MDs, which we can see and basically go through the very essential stuff. And I will quickly show you first off the docs folder that contains a bunch of readmes, which if you actually want to install Bitcoin Core or get into it, it's warm recommendations that you go through these files and actually see. I'll just show, let's say, the Windows README. This is how you set up the files, what you do with it, and we'll speak about Qt. This is visual interface layer of the whole Bitcoin. Pretty all the other stuff is self-explanatory. Here we have free BSD systems, Unix, OS X, and everything else that's needed. Basically, to install a Bitcoin Core, first off, you have to figure out your own platform. You have to pick up all the dependencies, general dependencies, and some tools used to actually build any C++ project. Aside from it has we'll see a bit later what Bitcoin build system builds, but there is a one thing called Bitcoin CLI. It's a basically command line tool that we can use to sort of talk to nodes and everything behind it. It exposes the JSON RPC. We communicate it with the nodes to that interface, and of course, we can always introduce the REST interface. I won't be going through the stuff as you can see. There's a lot of documentation here involved. So some of the also interesting sources before we go into the main one would be the tests. I haven't explained on a networking layer that Bitcoin, when it spawns its network, there are basically four types of network: main network, test network, done in two variations, Signet, which is a special type of testing network, and regression test network. All of these stuff, because Bitcoin is a very complex project, and you have to run a series of both integration tests and unit tests to make sure everything works. And they're being divided into such categories, which again I won't be going through. But they can easily be invoked from the general command line, like make test and everything flies, so to say. We have dependencies folder. I'll just show you that README file. Nothing strange here. So these are some triplets, like a combination of where the Bitcoin can actually be installed, and as I said, the dependencies, and this is a special case for Windows and all that. So if you want to start with Bitcoin, go through the docs folder and installation stuff. Now, without further ado, let's dive into the source folder. As we can see, things are both logically and ordered here with the, let's say, image folder, crypto folder, all the cryptographical elements that I've mentioned. Let's actually jump straight in. What we can see here are pretty familiar header files and implementation files of different hashing algorithms. AES is hashing. Chachapoly is also a hashing algorithm done by Google folks. There's a hex, HMAX, that I've mentioned. It's header message authentication and its variations using the SHA family of algorithms. MooHash, also done by Google. Entire SHA family from SHA-1 to SHA-3 with all the variations and the usages to 256. And lastly, we have a SIP hash, which is another hashing algorithm here. So quite a lot of hashing algorithms in Bitcoin. Let's see, for instance, the CRC32, that's another hashing algorithm, common redundancy check. That's what CRC means. And we have pretty, let's say, standalone implementation of the CRC, which is, as we can see here, collects a few other CRC32 implementations under an umbrella and basically publishes everything or uh, is aligned with this RFC. I won't be going through because it's a lot of the stuff, but this code should be self-explanatory. How we create a buffer and how we can do this stuff, basically. Init folder. This is how everything starts. As I've mentioned, when build system runs, these are pretty much the outputs. We have a Bitcoin GUI, which is done through Qt. Qt is a framework done by Nokia, and Bitcoin developers have decided to use that as its internal GUI platform. It is connected to 0MQ, which is not to be found here. We have a Bitcoin D, which is a main process, or basically Bitcoin node. There is a distinction between Bitcoin D and Bitcoin CLI. Those are two different outputs. We use the later one to communicate with the Bitcoin D. Bitcoin D actually being that network or nodes or mining or whatever they call it. Technically speaking, that's a Linux daemon or something that you can put in Windows as a background process. And of course, you can communicate with it. Haven't shown you the common implementation or common file that contains some of the common stuff used throughout the project. We'll see something that may be very interesting here. This is called the kernel of the whole system. This is actually quite interesting file. Let me show you something. Uh, every blockchain, as they say, it has its own Genesis file. Genesis is the way how something is created or like the very beginning. If we pay attention to this string, this is something that has been put in the Bitcoin core. And that's why some of the folks believe that the Bitcoin is actually a response to the central banking system, alluding to that crisis that I've mentioned at the beginning in 2008. What we see here is actually the Times Magazine from the January 3rd, 2009, that basically had this as a leading title, that the chancellor is on the brink of a second bailout. Bailout is another jargon when basically governments or other institutions help banks who are basically on the verge of a bankruptcy. And that's something that Bitcoin crew does not love. And it's what's been placed in the kernel inside of the Genesis file as a starting point. We hash this message, and that's how the very first block is actually created. It's called create Genesis block method that's used during the initialization. This is an example of the things that I've said, like what's the distinction between mainnet, testnet, and all the other networks. Basically, this in this file, we can set the things up. Consensus is something that I haven't touched base too much. That's the way how the network is actually synchronized. They call that a mining process. And here we can set certain checkpoints or BIPs as the Bitcoin grows and evolves over time. You're allowed to include or not include certain improvements inside of a network, which down below I'll show you how you can avoid when you're dealing with the test network. So you basically remove all that or just enable or that or disable the mining so that you can test certain stuff. Even though if it looks like a bit weird and too many settings, at the end of the day, it's nothing quite uncommon. We're just setting some structure and are setting the whole blockchain network the way we want. I will show you also a few more interesting things. When we create the Genesis block, this is the amount of coins. I will show you what the coin is actually awarded. This is what they call a mining fee reward. And basically, you could set it to be whatever you want. At the beginning, it was set to 50 Bitcoins. And over time, the network, I also haven't touched base on that, has its a thing called halving. So every now and then, this 50 coin reward gets halved. So it's 25. And after third halving, today is 12.5. So one quarter of the original mining reward. Eventually, Bitcoin will run out of the mining rewards and will become zero. And that's something that we can actually test in the make in the test network and experiment with that. So basically, at some point, no one will earn by mining the Bitcoin, believe it or not. Um, so all the other stuff here are maybe not that important, especially after all these talks, where you can set those checkpoint data. It's basically the way how you ensure that all those PIPs are in place that we have seen here at the top. Uh, Feel free to browse this at your own pace. I will just be going through. This is the way how we can create a test network. Test network basically replicates the main network. It's just a little bit sort of free to use. And again, we have awarded a 50 coins reward here for anyone who mines on the test network, which could be yourself if you're spawning the Bitcoin node. Two more networks to go through. Network 4, until recently was network 4. This is a sort of variation of a test network that you can use for different things that just replicating the main network. Primarily, the Bitcoin security group uses this network to test certain security novelties or new algorithms and so on. Signet is a special type of network that you use just to check the signature, as basically all the transactions, as the Bitcoin calls it, are consistent of digital signatures, just a bunch of them. And if you want just to extract a whole system and just test how your signing goes, you can spawn a Signet network, basically. Lastly, we have a regression test. This is something that it's used to basically check the entire system. So whatever new has been put in the Bitcoin, you run several Python scripts and some other testing suits, but you do not touch the main network, nor you do on Signet. You do it on a regression test network. A little bit of explanation, as we can see, always active unless overridden. So it's basically give me everything that Bitcoin has. I just want to test like entirety of the system. So that's a kernel and quite a lot of interesting stuff inside just the one file. I won't be going through, but I will just try to explain the level of seriousness that we can see here. This is a mempool implementation. So basically, a Bitcoin deals with the memory in its own way and respecting all the possible problems that may arise in that approach. Um, this is the kernel. I'll show you just a few more folders and then we're done. Uh, this is one specifically designed elliptic curve. It's called CACP256K1, pretty cryptic name. But let's see what the README says. It's a high performance, high assurance C library for digital signatures and other cryptographic primitives on specific elliptic curves. The library is intended to be highest quality, publicly available library for cryptography on SACP curve. The primary focus now has been usage in Bitcoin system, and usage, unlike Bitcoin, may be less well tested, verified, or suffer from a less well thought out interface. So this again explains the very high level and devotion of certain cryptographers to achieve the very best of the best in and put it in Bitcoin. And here you can just see this is basically a C library, and it can be used even in the embedded system. And of course, it conforms to these BIP improvement proposals. So that's elliptic curve. Oops, went too far. I'll show you a few more things. Wallets and utility stuff. Wallets are a way how we communicate with the network. That's if you remember that picture of a distributed system, there's one more thing to be added on it called the wallets. We can create the wallets using the Bitcoin CLI. So when we build the entire stuff, we can achieve that using the CLI. We can basically create an endless amount of wallets because there's just the public keys, believe it or not, and they get hashed using the base 58 encoding. They get double hashed so that you can transfer them pretty much everywhere or across the globe. I can give you my hashed wallet address that won't reveal my private key sitting behind it. So this is a whole section of how the wallet is implemented. We had tests here. And as I've mentioned, the RPC is the way of how we communicate with it. So that's been wrapped here, just a quick glance of how you sign the messages, send them, and do the backup of it. So security procedure. Again, I won't be going into all the details. Here you can see what all the aspects have been covered. Loading mechanism, receiving, sending, and everything has been secured. There's a concept I forgot to tell you that's called double spending problem, which is solved. Basically, you cannot double spend single Bitcoin. If you spend it, it's done. Not a single one on the network can do it. And we have one complete section that I've completely omitted. It's called the storage. Probably we don't have enough time or maybe concentration because this is a huge thing. Remember, I told you some people write books about it. Would have to speak about Merkle trees, about binary trees, how that is serialized and then deserialized in every single transaction process, which we won't be doing today. I will just mention that Bitcoin takes sort of a key value storage approach. So the data is not structured generally, as we know in structured computer language. No, it's binary tree slash Merkle trees. For that occasion, it uses a thing called level DB. That's a key value storage done by Google. And it originates from the project called Berkeley DB. It's a very high performant key value in memory or in storage mechanism here. Again, it's inside this code base, but on this talk, I won't be going through it. Very last thing, and we're done. Don't worry. Uh, I wanted to show you what uh, some project of this size, maybe this is not, hold on. No, it's not. It's older. No, this one. This is what I've been saying. This is a level DB. And you can see by the title, it's done by Google and what's the whole purpose of it. But again, maybe some next time. This, I hope, was more than enough for just the beginning. We haven't even talked about a thing called UTXO, which is a huge concept. It's called unspent transaction output. We won't be addressing here today. And the whole those security improvements that I've mentioned as VIPs. So basically, after everything, I just want to give you a couple of yeah closing thoughts. So what we are seeing here is pretty a massive open source project. In my humble opinion, we can put it into uh, like order of one Linux. that's been developed for more than 30 years. It contains more, believe it or not, million commits, and we know who is behind everything. Here we have a similar example, 15 years of active development, pretty high standards, devotion to details, and something that probably as Linux will influence us all. That will be all. Thank you for your concentration and listening. Until next time, happy coding.
Yeah, so so you showed some examples of the libraries that are in the code base. Are they forked and developed independently at some point, or are they regularly pulled from upstream?
It's mostly in the contrib folder we have. I'll show you that in a second. We have all the not here again. To answer your question, they typically ask us to fork the stuff, and let me show you. It's an interesting thing when speaking about the forks. So as we see, there's an active number of 36,000 forks. So that sort of answers your question. But also one thing, if we get to know that cryptocurrencies and all that, most of them were actually just the Bitcoin forks that partially explains this huge number. The numbers went from 9,000 forks to 12,000 active cryptocurrencies at some point. If we take into considerations that only like 5 or 10 are now available, and that everyone had the chance to actually fork, exchange the parameters, and create their own coins, we could actually observe one different mathematics. 99.9 of them failed because we have 36,000 forks and just 5 of them are on the market. That means that 36 point something didn't make it. So the crypto sphere is definitely 99.9% failure chance for all everyone who is in it. That explains the number of forks. More questions?
Yeah, sorry. Uh, Actually, I asked about the library. So you showed, for instance, Level DB. So is it maintained independently from Google's Level DB, or is it actually pulled from upstream?
Both ways. Level DB in specific is just pulled from the upstream. And as we have seen that special elliptic curve that's specifically designed just for the Bitcoin. So it's part of the whole code base and you can fork it.
Okay. Okay, cool. Um, there is a math behind this, as we said, and how is it justified that math is programmed properly? Of course, there is testing intense, as I understood, and are there some mathematical way of proof of coverage test or something?
Okay. So there are two types of general types. Functional testing, like when we want to make sure that, let's say, when we spawn the wallet, it actually is created and it's registered in the system. There's several different ways how we can do the transaction in Bitcoin. Let's say from one account to another. We can do group payments. For instance, 5 of us can actually transfer something to, and we can do payments for third-party accounts. So let's say if I buy you a drink, I transfer my money to some fellow, you get the drink. So those stuff are tested on those testing networks. On the other hand, cryptographers use mathematical proofs, like as a mathematic it spins around proofs, to use that as a claims. Sort of, here's the proof. I'm just saying generally. Here's the proof that I have a good hashing algorithm. Is a collision resistant. It's not prone to all the possible attacks, which are computational slash combinatorial mathematics. Maybe that could answer your question. Like cryptographers hide behind that and use that to sort of claim, okay, my hashing algorithm is quite secure because of the mathematical complexity behind it. They not necessarily test it. They sort of uh, what's the word? Um, they just do that out of their heads. You can do it on a piece of a paper, basically. You can prove certain.
Okay, I see. From what I understand, so mathematics invents some algorithms in mathematical formulas, then transform it easily to some more hardware checkable and then implementation. So then they improve performance, and they said that basically that's not far from math formulas, and we can see as a whole thing this algorithm. So that counts as a proof. Something.
Thorough. Yeah. There are two ways more, maybe in some other talks. Cryptography uses some a portion of mathematics that claims that some things are unprovable. So that's higher order math. There are even some mathematical conflicts on that field. One of which was done by, let's say, Bertrand Russell, even though he's can be considered as a philosopher or perhaps even a writer. He figured some logical problems in fundamental math, and he called it Bertrand Russell paradoxes. So there's a whole class, let's say, that mathematics called millennium problems that have originated since I think end of the 19th century. They're still unsolved in the math. A part of that is taken by cryptography. It's like, oh, okay, no one can solve this. Okay, that means that some things cannot be decipherable, like not computable slash not decryptable to some extent, of course. But again, cryptography is there's no perfectly secure system. Just so we know, we can hide behind either randomness or computational complexity is the two main ways in cryptography.
Okay, there are another two questions. I heard zero trust or something theory. It's one question. Can you say about this?
Absolutely.
And the third question. So, do academic mathematicians um, um, work on something in Bitcoin, or they seems should be some? Do mathematicians nowadays provide some new theories, new works to implement on Bitcoin or maybe other?
Yes. Okay, so the first question, what about that zero knowledge proof? That's how that scheme is called. That's part of the cryptography, known for about more than a decade, but we have been waiting to have a specific implementation. More importantly, the use case. Like we've known that in theory, but we were waiting for some valid way to do so. One of the blockchains utilizes that's called the Polygon network. Everything that runs through the network is actually also additionally secured using the zero knowledge proof. And as the name suggests, you can have a mathematical proof that hides pretty much everything behind it. So you can prove, for instance, that uh, one element it belongs to one set, like set theory, basic set theory. If all the apples belong to fruits, so to say. That way you have a proof combined from the set theory and some mathematical stuff that you know the element, but you don't necessarily have to know anything else about it. It's called zero knowledge proof. And that is used and can be used maybe on a Bitcoin level. That's part of your second question, which goes like, if I understood well, are the current academics aware of this? Yes, of course. They're called cryptographers. So how do you get into that field? You typically study mathematics and then you specialize in cryptography. Whereas cryptography heavily used is in military services. And we may know famous Enigma. It's a crypto typing machine from the Second World War. Who has done that? Mathematicians. And in that case, it was a modular mathematics that ran 5 different disks. So when you type something in a keyboard, it actually encrypts the data. So it's mathematics since like the the beginning of time. And yes, they are aware, quite aware. And the very last thing is that emergence of the Falcon quantum resistant algorithm. That's typically done by institutes.
So you mentioned that Bitcoin is a peer-to-peer network, but even a peer-to-peer network has to start somewhere. So when you start your node, uh, how does it know where to start connecting to peers to find out about other peers, and who actually controls those nodes?
The nodes get produced from the publicly available source code. So when we built the source that we have seen, we use that Bitcoin D thing. You can run it as a daemon basically, and that partially answers your question. So like you dedicate certain machine, it can be in cloud with some server, whatever. You install that file on an executable basically, and then you run it. You have ways to configure it using Bitcoin configuration files, like on what port it will be, what sort of connection will it listen to, and everything else, where it will store the data, what will be the output directory, and so on. And all the nodes I haven't gone through may be divided into just the hashing nodes, nodes that do what's called full nodes, like they contain the data and they do the third thing that you have asked. They sort of, in a brief way, contain the DNS tables of other seeds. So you can basically create a file. Here's the initial, pretty much known and known in advance public IP addresses where you put original node to start the network. So it's a bit of network configuration, basically.
So it's hard coded, right?
To some extent, yeah. You can load it from external file or you can hard code it, yes.
Okay, thank you.